Okay. Hello once again. I just thought to complete the idea or the material of chapter 7, simply because we have the coming 3 lectures. We need to focus on chapter 8 and chapter 8 mainly, since this is the only material that is remaining to cover, and you do have a quiz next week on that material. So let me just continue the idea of chapter, or the material of chapter 7 in this case. Just to remind you with what we did in this chapter, we reached up to the story of nozzle, because under ductive flow we agreed to have the nozzle, the piping system, and the throttling valve, and these are the ones that has been covered last lecture. Today, I want to talk about the other 2 types of flow systems that supposed to be covered here. One of them is the expansion devices, and the other ones are the compression devices. With expansion devices, the first one here is the turbine. Now, if we thought about what is the turbine, we already mentioned before that with the turbine, we normally have reduction in pressure. But if I want to make the idea clearer here, I would just take you back to the nozzle. If you think about the nozzle, what's happening there with the nozzle was that the enthalpy, or the internal energy, that energy is reduced so that we can have more velocity at the outlet. So in other words, the internal energy, or the enthalpy, is converted into kinetic energy. Now think about it like this. If I brought at the outlet of the nozzle, if I brought a blade and I connected that blade, or rotating blade, to the nozzle, what will happen? Because of the kinetic energy at the outlet, then the nozzle will rotate, and the blade will rotate. So what's happening here is that the blade will be rotating because of the increase in the velocity at the outlet of the nozzle, and in this case I will have work that comes out. So the idea of the turbine is just kind of combination between nozzle and rotating blades together. So the alternative set of the nozzle and rotating blades is actually the turbine. Okay, so what we have in the turbine is simply that kind of conversions from internal energy, or the enthalpy, into what? Into not into kinetic energy, but into work. So what we have here, we are getting work out of the turbine. So that's why the turbine here, it's a work producing device. And because of such kind of conversion, we do have what's called efficiency. Efficiency because efficient conversion of that energy of high pressure inlet, it will be resulted in a work that we get at the outlet. Having very efficient conversion means I have more towards the reversible process, as we said before. And the question here is, what's the difference between turbine and expander? Because I put them both in the title, and I was talking about turbines up to now. Actually, it's just a basic difference. If you have a steam as a working fluid in the turbine, and this was the motivating force, I mean the fluid that causes the work to be produced, then we call it turbine. But when you have high pressure gas, okay, where you don't have steam here, you have gas like ammonia, ethylene, that are used for chemical processes and petrochemical processes, then in this case we don't call it turbine, we call it expander. So expander is same as the turbine, provided that the working fluid is not steam, it is high pressure gases like ammonia and ethylene, as I mentioned. So that's just the basic difference between the two. All of you knows the first of thermodynamic. I already explained it for the turbine, and we cancelled the kinetic energy terms, we cancelled the heat transfer considering adiabatic, then no change in potential energy, then we will have the power equal to m dot delta H, provided of course that I have one inlet, one outlet. Okay, and this is the general type of turbine. Now the isentropic condition for the turbine is when I have isentropic work that is produced. In other words, S1 is equal to S2, and that that work for asentropic, it's called delta HS. It means it is H final minus H initial, but H final based on asentropic condition. In other words, we normally call it H. Here it is H2S minus H2. In other words, this is H final based on asentropic condition. And as you know, the asentropic work is actually the maximum amount of work that we can get. Why is this? Because the turbine, when it works at its best condition, means that it is reversible, and if it is reversible and there is no heat transfer, means I am getting most of that kind of conversion between delta H to work. So that's why I'm getting maximum amount of work when it is reversible adiabatic. And this will take us to the efficiency relationship that we mentioned before. We already mentioned that with the efficiency, it was W. Here I have work producing device. So it is W irreversible over W reversible. This is what we said before. Now you can just call it here W, that is the W of irreversible is W actual, and W reversible is W asentropic. In other words, it's equal to delta H over delta HS. Okay, delta H here represents the change in enthalpy based on a reversible process, which is actual, while delta HS represents what? Represents the reversible process, which is reversible adiabatic process here in this case, which is asentropic. Okay, and that was clearly mentioned here as it's given the efficiency equation. Delta HS is the asentropic, and that's why it is this ratio. Now, for your information, normally with the turbine and expanders efficiency, it ranges between 0.7 to 0.8. This is what you have in reality. Okay, this is the range of the efficiency. Now, I want to show you the HS diagram for that. Why is this? I want to clarify how I got delta H less than delta HS according to HS diagram. Now, if you consider what's happening with the turbine, with HS diagram, it is directly proportional relationship between H and S at different pressures. So here, if I consider, for example, state number 1, which is 0.1 over there, now what's happening with the expander? With the expander or the turbine, we got reduction in pressure. And because of that, you are moving from 0.1 to 0.2. Now, if that change or that reduction in pressure took place in asentropic manner, then you would have this dashed line. So the dashed line here means I don't have any change in delta S. So delta S is equal to 0 between 1 to 2 dash. 2 dash means the final condition at which you have asentropic condition. In reality, what do we have? We have the shift from 1 to 2. And if you want to consider delta H means the y-axis, then delta H is going to be only this y-axis interval between 0.1 and 0.2, this one. Okay, and you can see it is much smaller than delta HS because delta HS is moving from 1 to 2 dash, and that's why delta HS, which is the change in enthalpy based on asentropic process. So you can clearly see that delta H is less than delta HS, right? And the efficiency is simply the ratio between the two. Okay, so this just shows that the more irreversibility means that this ratio will be higher. When delta H is much smaller than delta HS, then I will have more irreversibility in the process. So that is how to get that on the HS diagram. And you can see there, delta S is equal to 0 if you move from 1 to 2 dash, but between 1 to 2, you have at 0.1, you have S1 here. At 0.2, you have S2 there, and there is delta S simply because it is not a reversible adiabatic. Okay, so that's basically what's happening with the turbine. Now, if you understood the turbine, then the pump, the compression system. But now here I'm just talking about the expansion system, which are the turbine and expanders. The compressor is exactly same but opposite in terms of concept. So what I will do, I will go now to explain the the compression devices, and then we'll start solving problems. So I'll skip the example of the compressor of the expander or turbine just to show you what's happening with the compressor. Then I'll go back to the problem. With the compression, it is exactly same as the turbine, but everything is opposite. What do I mean by everything is opposite? Number one, I want to emphasize on the fact that with the turbine, with the turbine, the flow chart for the turbine was that you have an inlet, okay, and the pressure is reduced at the outlet. Sorry, I'm talking about turbine. So the drawing of the turbine will be taper shape, but with that larger region here compared to the inlet. And why is this? It is simply to represent the expansion that take place. And that's why what you have normally is that P2 here is less than P1, okay, with the expansion. And as a result, you get a work that comes out of the turbine. This is how it is. This is with regards to the turbine. Now, when you look at, or the compressor, the expander, when you look at the compressor here, you can see just the opposite. You have the inlet bottom there, okay, at P1, and then you get increase in the pressure, and that's why P2 here is what is greater than P1, because it's compression device. With the compressor, it's work consuming device, so here I have the work that gets into the system. Well, the idea here is that just the scanning, but that's why we put W in rather than W out. You can see what's happening. So that's basically how it is. And in terms of the taper shape, because of the compression, I got it just opposite. The shape here is just smaller, the outlet compared to the inlet, just to show or to express the compression itself. Keep in mind, the cross-section area is not changing, neither in the turbine nor in the compressor, normally, or generally. But that reduction here just to show compression and expansion process. Having it smaller or larger at the inlet or at the outlet in terms of the drawing. Okay, so that's in terms of the sketch or the flow diagram of the turbine and compressor. Now, in terms of what's happening, it is just opposite. It means that with the W asentropic, it's still delta HS, but this is not the maximum work you are getting. If it is asentropic, then this is the minimum work we are feeding to the compressor. Again, it is ideal. It's called ideal because at best condition, we need to consume minimum amount of work. So that's why this is the amount of work. And because of that, efficiency is not delta H over delta HS like what we did with the turbine, but it's delta HS over delta H. Same as we did before, same approach. And again, the efficiency for compressor ranges between 0.7 to 0.8. You can see it's just simple in terms of the concept. But with regards to the HS diagram, it is again opposite. Before with the HS diagram, we were moving from 0.1 to 0.2, from top to the bottom, because the pressure decreases. Here from the bottom at point number 1, and then upon compression, we have the pressure increases. And again, if it is actual, then it's no longer asentropic. I have delta S. But with asentropic condition, I have it moving with delta S is equal to 0. You can see there. Delta is equal to 0, and I move from 1 to 2 dash. And this will show, again, delta H and delta S is over there. Delta HS is between 2 dash and 1. Delta H is between 2 and 1, because this is the actual. Delta H is the actual, while delta HS is the reversible adiabatic one. Okay, and you can see delta HS is smaller than delta H, and this represents the efficiency of the compression device. Okay. So that's basically what we have with the compressor. So if you understood the compressor, the turbine, then the compressor will be piece of cake and it's easy. All right. So now, just as an example or elaboration on what we did so far, I will show one example on the turbine to give you the idea of it. And then I will leave the other example, which is for the compressor, for you to practice. Here what we have a turbine so I'm just going to draw the schematic diagram for the turbine. So here is the turbine, and I have the inlet out. Oh, sorry, that's not a nozzle, so I have to draw it. Here is the turbines, and then I have the work that is out of the system. Plus, it says here that the turbine's rated capacity is 56,400 kilowatt. That is simply the work that comes out of the turbine. So 56,400 kilowatt. This is the power out of the turbine. And the inlet conditions were given as P1, which is 8,600 kilopascal, and temperature T1 equal to 500 degrees C. Now, what they said here, they said that this discharge into the condenser at a pressure of 10 kilopascal. So the final pressure here is 10 kilopascal. And what we want to say here, it says that the efficiency of the turbine is 0.75. So I do have here efficiency for the turbine, and that's equal to 0.75. Now, the question here is this. They were asking for the state of the steam at the discharge. So this is the first requirement. What is the state at the outlet? And they were asking for the mass flow rate of the steam. So it's two requirements. What is the state at the outlet? and what is the mass flow rate of the steam. Now, remember one very important thing. At the inlet, since I have two properties, T1 and P1, I can fully define the system. I have no problem. It is a steam, and I have the steam table. I can get the properties, and that has already been covered in chapter 6. But the point here is this. I don't have other than one property at the outlet. I cannot fully define the system as they want in number 1 here. They want me to define the state. I cannot define the state like this. And then, what is the relationship between the inlet and the outlet? Did they mention in the question that it is مثلا reversible adiabatic? No, they did not. How they did not? Because they give me the efficiency. If they give me the efficiency, it means definitely it's not reversible adiabatic. Okay, the efficiency equal to 0.75 means this one is the ratio between delta H over delta HS, or it is the ratio between W dot actual over W dot reversible, or actually asentropic I will call it because it's reversible adiabatic here. Okay, so that's basically the efficiency. The good news is that I have the efficiency. I don't have here other than one information, but we can do the following. Listen carefully. Since I have the efficiency, why don't we get delta HS? And delta HS means what? Means delta H based on asentropic. I know my process is not asentropic, but when I get delta HS, I can use this relationship to get the actual delta H. Okay? And this is going to be very useful because I'll be able to define the outlet state. At least I will be having H2. And having P2 and H2 can help me fully identifying defining the state at the outlet. So the procedure will be as follows. First thing, at the inlet, I do have P1 and I do have T1. So when you go to the thermodynamic tables, you will notice that it is superheated. So that's why what I did, I found H1 and I found S1. And then, Doctora, why we need H1 and S1? Listen, you will need S1 because you would say, for asentropic condition, S1 is equal to S2 dash. And what is S2 dash? It is S2 based on asentropic, because in reality, I don't have asentropic, but I'm just considering if I have asentropic, then S1 is going to be equal to S2. So that's why I called it S2 dash, not S2. Okay, then at P2 and S2 dash, you will be able to define H2 dash. And if you define H2 dash, you can substitute it to this equation and you can get the actual condition. All right. طبعا after you get the actual condition, which is delta H, of course H1 you know it. That's why we found it here. So if you have H1, then from the fact that delta H is H2 minus H1, and I do have already delta H, then I can find H2. Then at P2 and H2, you can define the system. This is the procedure. But let me show you how to apply that. What I did, I got H1 and S1, and then I said for asentropic condition at P2 equal to 10 kilopascal, and S1 is equal to S2 dash. This is not S2, this is supposed to be S2 dash, because in reality I don't have S2 that is equal to S1 here. It's not reversible adiabatic. So for asentropic process, if it is asentropic, then S2 dash is going to be equal to S1. And in this case, what you have to do, you have to go to the thermodynamic tables and check this pressure. Okay, at this pressure, which is table F2, is this S is between S liquid is vapor or greater than S vapor or less than S liquid, so that you can define the state, which we covered in chapter 6. But here in this question, what I did, I went to table F1 and I had to do interpolation because I don't have pressure of 10 kilopascal. Okay, so I had to do interpolation to check. But if I were you, I wouldn't do this again. Actually, I should easier go to table F2 at a pressure of 10 kilopascal. Okay, check your S2 value. Is it between S liquid and S vapor? And actually you will find it's in between. And if it is in between means it is what? It is saturated mixture. طبعا, this is not the actual state, but this is the state based on asentropic condition. Remember, so for that reason, what I did, طبعا, if it is saturated mixture, you need to calculate what? You need to calculate the quality. Because if it is saturated mixture here, you cannot solve without knowing the quality. You cannot get the other properties. So what I did here, remember, I want to get delta HS. So now what I want to do, I want to get H2S. Okay, or H2 dash. You can either call it H2S or H2 dash. So to get H2 dash, I need to know how much X2 dash, how much the quality. So what I did here, by knowing S2 dash, knowing S liquid and S vapor, I substituted to get the quality based on isentropic condition. And I used this quality to get H2 dash. Keep in mind, this is H2 dash, not H2, because knowing H2 dash will help me to calculate this delta H S. Okay, so we substituted here to get delta HS, okay, from H2 dash that we calculated, and H1 that we already found it in the previous slide here. So for that reason, I just substituted in the efficiency equation. The delta H dash that I got, when I multiplied it by the efficiency, I will get the actual delta H. In the question, if they ask for delta H now, it is ready, I have it, but they did not ask for delta H only, they actually ask for the definition of the or determination of the state at the outlet. Yani still I need to find a property at the outlet. Of course, at delta H, since I have it and I know H1, I can get H2 because delta H is equal to H2 minus H1, and now I do have H1. I do have delta H, so I can get H2. So what I did here, I found H2 and it was 2436. Now this is the actual enthalpy at the outlet. Remember in the question, I have a pressure at the outlet and now I found the actual enthalpy at the outlet. Those are two properties. Now I can fully define the system. How is this? Again, go to table F2, at a pressure of 10 kilopascal, and H2 is equal to 2436 kilojoule per kilogram. You have to define the system and you will find it saturated mixture. And it is saturated mixture, but I cannot say that the quality is same as before. No, I have to find how much is the quality in case they ask me to get another property. And here what I did, I used the same information. I got H liquid and H vapor from the table. I substituted, I got the quality. You can see there, this is the actual quality, which is 0.9378 compared to the quality based on isentropic. Based on isentropic, it was 0.8 something. Now it is 0.9 something. And in case, in the question, they only asked us to define what is the state. And by saying it is saturated mixture, خلاص, we finish the question. But this step that I did here, just in case they ask, for example, calculate S2 at the outlet, or calculate U2 at the outlet, or calculate specific volume at the outlet. But U2, I meant the internal energy here. So you have no problem because once they get the quality, substitute in the major equation, which says that M liquid is equal to M, which is any property you want to calculate, is equal to M liquid plus X MLV. Okay, so this is how you have to, or delta MLV based on some textbooks definition. So that's basically what you have to do. And remember in the question, they ask for two things. One of the requirement was to define the state, and we already defined the state. We said it's saturated mixture. But the other one was to know how much is the mass flow rate. Now remember, they give us in the question the amount of work, W dot. And if you remember, it was 56,000. Okay, it's work of reducing device. So that is going to be minus 56,400? Okay, kilowatt. Let me just double check that again. Yeah, it is, yes, this is the amount. This is W dot. But I know that this W dot is equal to M dot delta H actual, because this W is the actual power produced. Okay, so in this case, I will just put M dot delta H. And I can find this M dot based on delta H that I have already calculated here from the efficiency relationship. So it is simply direct substitution. We get the mass flow rate as around 59 kilogram per second. So this is how you solve if the efficiency was given. The procedures, I will say again, is that you will consider if it is asentropic, and then you will find S1, you will equalize it with S2 dash, and then at the outlet condition, at the given S2 dash and the other property, you will find H2 dash. Then you will substitute in the efficiency equation to get the actual property. Once you get the actual properties, then that is mainly what they need. If they need any other thing, at least the actual properties, you have them at the outlet, so you can fully define the system and find any other properties if needed. Okay. So same thing with the compression device. Here, I just will leave this example for you. You can just follow the same procedures exactly, except that with the efficiency, instead of multiplying delta HS by efficiency, here you will divide. Why is this? Because with the compressor, this is the basic difference between the efficiency equations of the compressor and of the turbine or expansion devices. So, but the other procedures are same in terms of procedures. Yani. Okay. The last thing I want to talk about in this chapter is what if the same question was given, the one that I just explained was given for ideal gas. It is not actual data. It's not from the thermodynamic table, but it is ideal gas. If it is ideal gas, it is same thing. Same thing means if you have been given the efficiency, for example, with the turbine, it's delta H over delta HS. And to get delta HS, what we had to do, we considered for asentropic process and we solved. Same thing here. For asentropic process means what? Means what? Mean delta S is equal to 0. And when you say delta S is equal to 0, that if you rearrange it, you will get that equation. If you remember, we already did such a derivation in the previous chapter. And I mentioned to you that this came originally from delta S equation. Then if you want to, once you found T2 dash here, then again you need to calculate delta HS, because in the efficiency you need to substitute of delta HS here. Delta HS value, it is simply CP mean H. Why CP mean H? Because you want to find delta H. But I called it CP mean dash H. Why dash? Because now you are going to substitute of the temperature T1 and T2 dash. This is T2 based on asentropic. Okay, into delta T, which is T2 dash minus T1. Okay, so this is what we did. And once we got this asentropic work, then you will substitute in the efficiency to calculate the actual, to get the actual. But from the actual itself, from the efficiency you'll get the actual, and this actual simply means it's delta H. So I have delta H in this case. In other words, if in the question they ask you, for example, to find the actual temperature, then all you have to do is just to rearrange the equation to get the actual temperature. That's it, basically. But what if they told you in the question that it is constant heat capacity? Constant heat capacity means what? Means I don't have mean at all. I only have CP. And when it is constant, there is nothing called CP mean H, CP mean S, CP mean dash H, CP mean dash S. No, all of them are same. Which means when I want to substitute in T2 dash equation, the one that I just found here, 718, okay, that CP mean doesn't matter whether it is CP dash mean S or CP dash mean H or CPH or CPS, which takes us what? Takes us back again to chapter 3, when I said when it is constant heat capacity, T2 over T1 is equal to P2 over P1 all to power R over CP. We already mentioned that before. And that CP doesn't matter whether it is CP mean H or CP mean S, because it was constant heat capacity. So did you understand why in chapter 3 we accepted this equation, regardless of what is that CP? Okay, this was the reason. But here I'm not calling it T2, but calling it T2 dash, because that is the asentropic condition that I am assuming, not assuming, I'm saying if it is asentropic, what will be the value so that I can use it in this relationship, which is efficiency relationship. خلاص؟ انزين طبعا you all know if I want to find W asentropic, it is CP delta T because it's delta H, but because it's asentropic, then it is delta HS or delta H dash. Okay, CP is no longer constant. If it is not constant, then you will put it as just CP. And I can do one thing here. I can just take T1 as a common factor. Then in this case, I would have CP T2 dash over T1 minus 1, because I took T1 as a common factor. And I can replace this ratio, T2 dash over T1, with that P ratio. And that's why you will get equation 722. Okay, this is just playing with the equation to show you how to get the asentropic work if you have been given the pressure ratios instead of temperature ratios. Yes? Also, you can play with it furthermore by, for example, replacing CP as a function of gamma. In other words, because I know that R is equal to CP minus CV, then I can do this. If you divided R over CP means what? R is CP minus CV, and CP I put it as it is. Now, if I just played with that equation, I would have it like this. It is CP over CP minus CV over CP. In other words, it's 1 minus 1 over gamma, because CP over CV is inverse here. CV over CP, inverse of the gamma. So in other words, it's gamma minus 1 over gamma, which I have it here. And why I did this? Because now I can replace R over Cp that is here with gamma minus 1 over gamma. And I can remove that Cp, and based on what I have here, R over Cp equal to gamma minus 1 over gamma. It means Cp over R is equal to the inverse, gamma over gamma minus 1. In other words, Cp itself, it is R into gamma over gamma minus 1. And this is what I did here. What I did, I removed Cp and I put instead of it R into gamma over gamma minus 1. Okay, and I'm sure you have seen this equation before in chapter 3, but I'm just showing to you here how can we get back the equations in chapter 3 if I have constant heat capacities. So this is basically the idea. Okay, with that I am done with the material related to chapter 7. Last thing I want to say is, okay, if the Cp is constant, then how much it's supposed to be? Okay, there is a rule for it. Normally, if you have monoatomic gas means gases with only one atom, like for example, argon, hydrogen, of course not O2, no, that is not monoatomic. This is 2 atoms. I'm talking about gas that has only 1 atom. With monoatomic gases, normally we considered Cp as 7 over 2R and Cv as 5 over 2R. In other words, R over Cp is 2 over 5 and R over C, that is for monoatomic gas, sorry. Maybe I have to clarify it in another way. Okay, for monoatomic gas, it is Cp equal to 5 over 2R. This is the one. In other words, R over Cp is 2 over 5. But if you have diatomic gas, yani gas with more than 1 atom, for example, oxygen, this is more than 1 atom. CO2, those are, this is more than 1 atom, but diatomic means 2 atoms, O2, CO, N2, okay? This, if you have diatomic, then Cp is going to be equal to 7 over 2R, or R over Cp is 2 over 7. Insane. What if you have other gases, okay, that other gases at moderate temperatures? So for gases like oxygen, nitrogen, and air at moderate temperatures, gases of greater, and that is only, as we said, this is only for diatomic and monoatomic. But if you have gases that has more complicated structure, like for example, ethane, if it is in gas phase, this is not monoatomic or diatomic. In this case, you cannot, keep in mind, you cannot consider constant heat capacity, and especially when the temperature changes high, and you cannot use this equation accordingly. That equation was only based on constant heat capacity. Here, it's only constant heat capacities in this slide. Okay, so that's basically the idea. And here, I want to clarify what would happen if I have constant heat capacity in terms of efficiency. And if I have a turbine, then the efficiency is delta H over delta H dash or delta HS. Delta H means what? Means Cp means delta T. But if I don't have a Cp that changes, then it won't matter whether it is Cp, yani Cp or Cp dash or Cp dash H or Cp dash S, it doesn't matter. Yani if it's not constant, then you're going to put Cp H. And here, if it's not constant, we'll put Cp dash H. And delta T here is going to be equal to T2 dash minus T1, while delta T there is T2 minus T1. But if I have constant heat capacity, then this will be cancelled out. And if it has been cancelled out, then the equation can be simply written as follows. Okay? I want to clarify one thing here, maybe one more thing. Efficiency is equal to T2 minus T1 over T2 dash minus T1. In other words, if I want to find T2, it's simply the efficiency into T2 dash minus T1, okay, plus T1. But that was what? That was for turbine. If it is for compressor, it's just the inverse. And when I say the inverse, means that here is for compressor. When I say the inverse, means it's going to be in the numerator T2 dash minus T1, while in the denominator is T2 minus T1. And if you rearrange it, you will get this equation. So the idea here is keep or make sure that when you have constant heat capacity, you don't put yourself into the complication of calculating the mean CPH or the mean CP dash H. So last thing here I want to do, I will solve one problem on the compressor, but based on ideal gas. So what we have here, which is the last thing, I have here methane, and that methane we consider it ideal gas. It is compressed adiabatically. You can see they said compressed adiabatically, but not compressed in a reversible adiabatic manner. No, not isentropically, it is adiabatically. So I have a compressor, okay, and with the compressor, I have the inlet, I have the outlet, and I have the work that is into the system, W dot. Okay, this is compressor. That's the idea of the compressor. So according to the given information, it's adiabatic process. They already give me the initial temperature, they give me the initial pressure, according to what you have there, and they give me the final pressure, okay, which is 560. So the pressure increases from 140 kilopascal to 560, okay, and this is expected in a compressor where the pressure will increase significantly. What they ask for two things. One is they want the work requirement, W, and then number two, they ask for the final temperature. Now remember, this one is ideal gas. It is not steam where I can use T1 and P1, go to the steam table and get the properties. Okay? So if this is the case, we have to ask ourselves, how can I fully define the system at the outlet? I only have the pressure. As we said, since in the question here, let me just finish it off. The compressor has an efficiency of 0.75. So if the efficiency is given, and I know for compressor efficiency is delta H dash over delta H, or delta HS over delta H, it means for asentropic property or for asentropic condition, I will get delta H dash, and then I will use it to get the actual property. Because this actual property simply is the denominator here is W, which they need in the question. So what I did, I said for asentropic process, delta S is equal to 0. So for ideal gas, I put the delta S equation, I substituted, remember, what I have in the question, I don't have the final temperature, but I do have the pressure ratio. So the only unknown is going to be T2 dash. And this is what I did. You can either use a program or you can use solver using the calculator. So I think you will go with that option in any assessment. And I already taught you how to use the solver. So when you substitute in the equation, you will find the, here I just rearrange it. I was trying to rearrange it to put T2 dash in one side. Why is this? Because using the solver, that equation is sufficient. But maybe using the iteration, you need T2 dash to be in one side. And this is what I did. I just rearranged it to you. The idea here is just substituting in the equation, which is a function of T2 dash, and then either using the iteration or solver, you'll be able to get the final temperature. This is just my Excel trials, and you can just use your own programmed calculator. Okay, just see what's going on here. Okay, I think it took me back. All right. Okay, so as I did, all you have to do is just to get the temperature, and I found this temperature here from the calculation, and the temperature was 397.37. Now, what is this temperature? This is T2 dash. This is the temperature based on asentropic process. طبعا, if I have T2 dash, then finding delta H dash is not an issue. Okay, how to get delta H dash or delta HS is simply CP mean dash H into T2 dash minus T1. This is how to get delta H dash. All right. So what I did then, I just calculated delta H dash. But remember, this delta H dash, you need T2 dash, which we calculated. CP mean dash H, you need T2 dash and T1. So it's just direct substitution, and this will enable us to get the delta H. Okay. And see how this delta H is useful, or delta H dash is useful. It's very useful because I will need it to relate actual with asentropic conditions through the efficiency. So I took this value, I divided it by the efficiency to get the actual, and this is what they need in the question. They need the actual work. And see, الحين from the actual work, what if I ask you to get the final temperature? Can we find it? Of course we can, because that delta H simply equal to delta H actual. In other words, it is CP mean H T2 minus T1. Okay, that's CP mean H T2 minus T1. In other words, if I do have T1 and I do have delta H, the only unknown is going to be T2 and CPH, and CPH is already function of T2. It means the only unknown is T2. So, and this is what's happening here. I just rearrange the equation, and for methane, I do have A, B, C, D values from the appendix. I have the equation. Upon iteration, I got the actual temperature. So you can clearly see that the actual temperature is 428.65. If I compared it to the T2 dash, which we calculated before, it was 300 something. So I can see that there is a difference, and my temperature has been corrected because of using the efficiency equation. So that's basically how to solve if it is ideal gas compared to solving using the steam table, which we solved previously. انزين طبعا that's the end of this question. And the second question here is, what if I change the question by saying it is constant heat capacity? There is nothing called CP mean H, CP mean S, CP dash Hess. There's nothing like those. It's only one CP. So in this case, this will no need to substitute in this equation to get T2. Okay, I already derived the equation that will help you to get T2 directly from here. Why is this? Because there's no calculation for CP means. And you remember when I did the derivation here, I already cancelled the CP. Where is it? Yeah, here. Now I did that derivation and I put delta H. Okay, delta H dash over delta H for compressor. Okay, we cancelled the CP from both sides, and that's why you get this equation. So same thing here. I'm just using the equation after being derived, and no need to put the CP, and we got the T2 as 432.11. In other words, if I assume constant heat capacity, I'm gonna get 432 degrees C, while here it was 400. What is it? Here it was 428. So there is a difference, and the percentage error is 0.8%, but maybe much easier to consider constant heat capacity, especially if the temperature difference between inlet and outlet is not much. Yani considering constant heat capacity might be acceptable. Okay, and here my inlet temperature, if you remember, it was around 300. And the outlet is around 400, so it's a difference of 100 degrees C only, which is the assumption of constant heat capacity was considered acceptable or valid assumption. Okay, after covering the compressor, I think I need to talk about the pump. And what's the difference between pump and compressor? In terms of operation, both of them are work-producing devices, but the major difference between the two is that with the pump, the working fluid is liquid. Okay, pump it deals with liquid, and the pump, it consumes work so that it is needed to deliver the fluid. Yani the pump itself, it's a work consuming device, like the compressor, it's work consuming device. But I need the pump because I need it for delivering. Yani you have a fluid in one place, you want to deliver it in another place, then you have to push that fluid. So that's why the pump is a work consuming device. Okay. طبعا in terms of the equation, since it has the same concept of the compressor, then W is equal to delta H again. But that W here is only equal to delta H if I have what? If I have adiabatic process. Q is 0. So that's why I have WS is equal to delta H. Okay. And the problem here is what? The problem is how to get W isentropic. Now, again, with the pump, there is efficiency. Again, the equation. Okay, again, the equation of the pump for the efficiency is delta H S over delta H. But delta HS means what? Delta HS means that you have to consider isentropic process, right? And then here we have a problem. Normally, with the pump, the inlet to the pump is liquid. And if I compressed it more, the outlet is going to be compressed liquid. And if you remember, if it was water and we use the thermodynamic tables, we already agreed in chapter 6 that the properties of liquid, remember, the properties of liquid, if it is compressed, as approximation, we go and get the properties of, if it is compressed liquid, and you went to the table, you have to take the properties of liquid as approximation for subcool. Does it make sense here? If I have a pump and the inlet was liquid, the outlet was subcooled, okay? Then, and we said that at subcooled, at the given temperature, you will go and get the liquid property. And if I got the liquid property as inlet and outlet, then how can I get W? This delta HS is simply H2S minus H1. If H2S and H1 are same, especially that temperature difference is negligible with mostly negligible with the pump, then this means that this term is zero, and that's why it's not appropriate to consider this assumption here in the work. In other words, getting the subcooled properties is not available in thermodynamic tables, and that's why we tend to do this approximation. For that reason, the way we are going to find the asentropic here is using this relationship. And where we got this relationship? Remember, we already mentioned a long time ago that delta H is equal to T delta S. You remember that? Okay, it's T delta S plus V delta P or VDP. Okay, and now I want to use this is general equation, of course. If I want to use this equation here and it is asentropic condition, then this term will be cancelled out. In other words, delta H is equal to V delta P, and this is what I did. And with the pump, we considered its liquid phase, so the volume is almost constant, which is same as the volume at the inlet, volume liquid. So WS for the pump, WS for asentropic process is calculated by the integration of VDP, and the integration of VDP is V delta P. And that is very useful here because once I got the volume at the inlet and I know the pressure difference in the pump, I can find the asentropic. This is the asentropic condition. You need to remember that I gave you two equations at the beginning of this chapter, and I told you those equations from chapter 6, and I told you for pump, please accept those equations that delta H is not equal to CBDT, but CBDT plus correction. And same thing with DS. It's not CBDT over T, but plus correction, and that correction to consider the effect of pressure in the system. Okay, this is how to calculate enthalpy and entropy for liquids. So those are the two new information or two equations here. Okay, to integrate this equation, if I consider Cp constant and beta, which is normally the case in the pumps, beta can be considered constant. And the volume is also constant because I have liquid phase and I can consider it incompressible here. Volume is not changing significantly, so I consider it constant. So in this case, upon integration, I would have CBDT can be integrated to become CB delta T. That all term is constant, then I would have the integration of it delta P. So that's basically what you have. That is delta H is equal to CB delta T plus V1 minus beta delta P. So that's useful equation. It helps me to calculate delta H actual, and for delta S it is Cp ln T2 over T1. Cp is constant, integration of dt over T is T2 over T1, and here you have minus beta, and delta P is going to be, Vp, the integration of it is delta P. And when we are going to accept those two equations, if the temperature change in the pump is very small, and this is normally the case with the pump, and if the properties are insensitive to change in pressure, and that's why those values we consider them are just constant and we took them out of the integration. So, conclusion, with the pump, you do need three types of equations. One equation is the one that relates efficiency, or delta H with the delta HS, which is called efficiency equation. The second one is how to get W asentropic, which is delta HS here. This is the second equation. Third equation is how to relate delta H and delta S together with liquid. Okay, if you know those three equations, then you can solve any problem. Just a quick illustration or a quick example here on the pump is this. Here I have a pump, so I'll just represent the pump here. Here is the pump. I have a temperature. It's fed. What I have here at the inlet, I have a temperature. The fluid gets in as 45 degrees C. And it says that the pressure is 10 kilopascal. Normally with the pump, the most important factor we need to know is the outlet pressure, because with the pump, it is pumping. So the main change here is that the pressure changes, and they already give me that the pressure is 8,600 kilopascal at the outlet. So from 10 kilopascal to 8,600 kilopascal. This is the pumping system, and what they did, as we did with the compressor and turbine, the efficiency is given here. It is here. First of all, W, work of the pump. They need the temperature at the outlet, and they need the entropy change, delta S. And for those three, I have equations. As I mentioned previously, in order to solve, the efficiency will be very useful because it will help me relating delta HS with delta H. خلاص? And then the question here, how to get delta HS? To get delta HS means at this T1 and P1, you will go to the table and get H1. You will need S1 because S2 dash is equal to S1. You will also need to know the volume, and I will tell you why you need the volume. Remember, in the previous equation, we said to calculate W isentropic, you need the volume or the specific volume here. So that's why what I did here at 45 degrees C, which is the inlet, okay, at 10 kilopascal, it was saturated liquid. So we got the volume, which is volume of liquid. So that's one. طبعا beta value and CP value is supposed to be given in the question in case you want to use those equations, which are those, because here those equations 725, 726 are based on constant CP, and beta value is supposed to be given for the pump, and this is what we had. I gave you beta value, I gave you CP value, so in this case it's just direct substitution. What is that? Here it says W for isentropic, we have to multiply the specific volume into delta P. I found the specific volume here from the thermodynamic table, which is table F1, because it was saturated liquid based on the pressure and temperature given. The pressure difference is given in the question. What I did, I just substituted, but to convert the final into kilojoule per kilogram, I just had to make conversions, which you should be aware of, because the pressure difference here in kilopascal, while the specific volume from the appendix, it is in centimeter cube per gram. So we just had to make these conversions. Then this will allow me to calculate what? To calculate the asentropic work. Sorry, up to here, it is the asentropic work, not the actual. So what I did using, and this is only the asentropic work, 11.57. Using the efficiency should allow me to get the actual. Yani up to here, it was W asentropic. Here we use the efficiency to get the actual, so 11.57 is the actual. This is actual. By the way, this S doesn't mean asentropic, it means of the shaft. WS means work of the shaft. Asentropic is the one that terms for, or that refer to reversible adiabatic. So WS is equal to delta H, and I got the value. All right, so this is the actual. And according to the relationship, now remember, I will remind you, you need three main equations. This is the first one for the work, this is the second one for delta H, and this is the third one for delta S. So you have three equations, okay? Again, I will repeat. You need three equations with the pump. One is the asentropic work equation, the other one is the actual delta H, the third one is the actual entropy. So what I did here in my calculation, I calculated the asentropic. Then using the efficiency, I calculated the actual. Now this delta H actual, I want to substitute it here. Then why, doctora? I will tell you. In the question, they ask for the temperature difference, and this delta H is related to temperature difference through this relationship. Beta is given in the question. Pressure difference, I have it in the question. CP is constant value, it was given in the question. Then all I have here is delta H, which I found from the previous step. So when I substitute, I will get delta T. Now look at the value. Delta T is so small, less than 1 degree C difference. And this is very normal with the pump. And that's why I said here it was based on the assumption that the temperature is just changing very slightly. The temperature change is very small. And this, based on that assumption, we had those equations. And I think you can clearly see that the temperature difference is very small with the pump. Is it? I'm done with the pump. In terms of calculating the work, calculating the temperature difference. If they want the entropy, again, I will bring the entropy equation and I will substitute here. Cp ln T2 over T1 minus beta V delta P. All the information were given. V, we found it from the table as we mentioned previously, so it's just a matter of substituting. Plus, and delta S, we get it as 0.09 kilojoule per kilogram. I'm done with the pump, and these are nature of questions that are normally given. Last part here is the ejector. And if you remember when I did the flow chart, I mentioned that with the compressing device, we will cover compressor, we will cover pump, and last thing is the ejector. But we will not solve problems of the ejector, just to elaborate on some kind of limitation in thermal. With the ejector, the idea of the ejector is this. Ejector is a device at which it is used normally to discharge fluid. How is this? When you have gases, for example, you have gas or vapor from evacuated space, and you want this gas, okay, you want this gas to be discharged. What you have, this gas to be discharged or move, you push it with another or compress it with another gas. So ejector remove gases or vapors from evacuated space and compress them for discharge at a high pressure. So this is the idea behind it. But if you look at it, it looks like kind of several nozzles connected together. So this is nozzle here and that is nozzle. In other words, ideally, if you applied the first law of thermodynamics nozzle here and then here, you should be able to find the properties needed. But that is not the real case. Actually, in reality, when you apply the nozzles equations, you will find that the result is highly deviated from the real values. And why is this? The answer is mixing. Whenever we are working, we assume that we have everything homogeneous, mixing is perfect, and that's why we solve using the thermodynamic equations, assuming that there is no issues related to mixing or fluid mechanics, which is going to be covered in thing 2 and 4. Okay, now this or the mixing itself has a significant effect on the answer, and that's why we cannot apply the nozzle equations. And according to what it says here, although the usual equation for nozzle apply, and generally you can use the equation of nozzle, the mixing process is complex, and as a result, ejector design is largely empirical. Empirical means you can get the equation from experiments, and that equation is used to solve ejectors problem. The nozzles equations will give deviations because of the mixing issue. So with that, I'm done with chapter 7. These are some suggested problems to solve. I think then next or by tomorrow on Tuesday we can just start with chapter 8, so that by end of this week we can cover the required material we needed for the assessment. Okay, I will leave you by now, and beginning of next lecture I will ask you if you have any concern on this material.